Perfect. Welcome everyone to my talk. I'll be presenting our work that was recently accepted to NeurIPS. It's called the Interpreting and Analyzing Clips Zero-Shot Image Classification via Mutual Knowledge. So here we wish to really give some insights into zero-shot image classification. How does it work under the hood? What are the mechanisms that cause this very impressive zero-shot capabilities of the clip model? But before I do this, I would like to stress that this is presentation is about interpretable machine learning, interpretable AI. For those people who do not know what interpretable AI is, basically, you have any machine learning model, you give it an input. It can be an image, a video, an audio, a text, whatever it is. Here, we're assuming that we have a vision classifier, and basically it classifies this image as a robin. An American robin is a type of bird. And now the goal of interpretable AI is to understand what basically led to the decision of a robin. So we want to answer the question, why did the machine make this decision? And typically what you have in explainable AI is something called a heat map, where you highlight the regions that were important or that influenced the model prediction. So here we can see that these are the regions that basically influenced the model to predict a robin. So I would also like to take the time to explain why should we really care about explainable AI. Lots of people in the community think that explainable AI is not important, or we should not really care about it. But here I would like to take just 5 minutes to answer why is interpretable AI such a very important topic, and why should we really care about it. I will present just maybe 3 use cases. The first one is a use case that has happened long time ago, somewhere around 2014 or 2015, just when deep learning started to kick off. So here, this is the Pascal VOC competition, where the objective was to basically classify an image, or sometimes you localize it. It's like an object detection task. So for all images of the horse, you basically had a watermark at the bottom left corner of the image. And this was because all of these images came from the same source. So the people who gathered the datasets basically took the images of a horse from the same source. And then they trained the model on these datasets, okay? And you, after training at inference, you basically get your correct prediction. This is a horse, okay? And perfect, then we want to understand why the model made such a prediction. And the reason was not because the model was really looking at a horse, but it's basically, the reason was that it was looking at the watermark at the bottom left. So because of this watermark is present in every single image of the horse, the model simply learns a shortcut, a bias, a correlation, that whenever there is a watermark, then this image is a horse, because this is a much more easier way for it to learn and make predictions and minimize the loss. So this has been unnoticed for years, and people were winning prizes and awards without really understanding what's really going on. So with explainable AI, this is one use case that really helped us. Also, if you analyze some images, you see that because the way we take images in our world, they can basically really learn biases. So for example, when you take an image of a dumbbell, you usually take it with the hand that lifts the dumbbell, but you never take the dumbbell alone. It's much more common on the internet to if you just type dumbbell on Google, you will usually see a dumbbell with the hand that lifts it. So basically here we see that the model did not learn the dumbbell as a standalone concept, but it also always associates it with the hand that lifts it. So for a model, a dumbbell is a dumbbell with a hand. This is obviously a bias that we also don't want here. And this can also happen in vision language models and multimodal models and any vision language model. But here I'm going to focus on the task of visual question answering, where given an image, you basically want so you're given an image and a question, you want to answer the question about the image. So here we are given this banana, and then we ask a question: what color is the banana? We give it to a VQA model, and the VQA model spins out the answer. It's yellow. But the problem here is that in most cases, or 80% of the times in the data set, you have yellow bananas, right? So basically, it's much more easier for the model to learn this shortcut of that bananas are always yellow. So you don't really even need to look at the image to predict the answer. You don't even need the image. You can simply answer this question by just looking at the question without any image. Why? Because of this bias issue. So at test time, for example, you have a ripe banana, a yellow banana, a green banana, and you give it to the VQA model. It, of course, answers yellow because of this bias issue. So this is obviously something we don't want to happen. And this is just the bias, what I have been explaining, but there are many other use cases. For example, we can learn from machines. We can learn how they think, right? There are some things that are really complicated for us as humans. Our brains are just not capable of doing them. But on the other hand, machines, and especially neural networks, are very good at them. And one very successful example is AlphaFold, which predicts the protein tertiary structure from its amino acid sequence. So by actually applying explainable machine learning, explainable AI on the AlphaFold model, there are some people that are working on this right now, you can understand what specific amino acids in the input has caused this tertiary structure. And of course, this has a huge impact in biology, in curations for illnesses, for cancer, and for many other things. So we can learn from machines the topics that, or some things that are just too complicated for us as humans. Lastly, of course, you have rights. The customer has a right to understand the decisions made by machine learning models. So, for example, if you have an AI model which is basically helping the staff to make decisions on loans, and then you have a customer data, you give it to the AI model, and the AI model says that we should reject this loan, then the customer has the right to understand why his loan was rejected. And if I'm not mistaken, there was a use case that has happened where they found that the model was rejecting some loan application because of the color of the shoe of the customer. I'm not exactly sure where this happened exactly, but just to show you that this is a very serious use case. Okay, so this is just the motivation of why we need explainable AI and why I think it's something very important and something we should investigate time in. But now let me jump to the topic of my work, which is CLIP. So CLIP stands for Contrastive Language Image Pre-training. Basically, given a set of images and given a set of text, which are paired with the images, you feed each of them to separate encoders. One is the vision encoder, one is the language encoder, and you basically minimize the contrastive loss between the positive pairs. So the positive pairs, the positive image text pairs should be close together in the embedding space, and otherwise they should be further apart. So what happens here is something very interesting. You have a shared embedding space for the images and the text, right? So you can encode images and text in a shared embedding space. And this allows you, of course, to measure the association between any image and any text. So for example, you have this image here, and you have a bunch of textual concepts. You can simply run this image through the CLIP vision encoder and run all of these texts, each one of them through the CLIP language encoder. And then you can, because they are in the same embedding space, you can perfectly measure the cosine similarity between them, and you can get the association between each image and its corresponding text. And because we have this capabilities, then we can basically formulate image classification as a retrieval task. So again, let's say that we have this image here. And now what we're going to do is we're going to take our class labels and This time, they're not discrete labels anymore, but they're textual labels, right? So we're just going to create a prompt out of these textual labels, and we're going to encode the image through the clip vision encoder, and then we're going to encode all of these classes through the clip language encoder. And again, we can simply measure the association between each image and all the other classes. And the class with the highest similarity, in this case, it's 0.84, is the predicted class. So just to wrap up, in normal classification, you have a vision encoder, then a classifier, which gives you the prediction. In clip, what you have is a textual format of your classes. You encode them with the language encoder, and this is basically your classification weights. So basically, you can think of them as you have an encoder for the classification weights. You have a generator for the classification weights, and then you basically encode the image and get the prediction. So this is the main difference between normal classification and clip classification. In clip, you simply have a generator for the classification weights. Now, the first motivation that I would like to go through is multimodal concept-based explanations. So we're going to consider the ImageNet datasets. And ImageNet is a coarse-grained dataset for classification. Since 2015, models really outperform humans on ImageNet because, for example, I do not know the difference between an African elephant, an Indian elephant, and an Australian elephant. But models do know the difference, and these are called distinctive features which the model learns about. So models that are trained for such distinctive features should basically perform well. Sorry, if you have a model that performs well on ImageNet, which it means that this model is learning really distinctive features of the object, right? But let's say we have this image and we ask what are the discriminative features that the model learned for this image here. And when we, for example, when I say distinctive features, I mean the beak, is it the orange breast, is it the white belly, is it the black back, and so on. These are what we call as distinctive features, which basically distinct the objects from each other. So these are what distinct a bird from other birds, for example. And then if we apply some explainable AI techniques, what we get is a heat map. And obviously, this does not answer the question. It does not tell us what distinctive features were really important for the prediction, right? And even worse, whatever type of bird you have, a goldfinch, a junco, a brambling, a robin, they are all the same thing. You simply get you simply get a highlight over the whole main object, but it doesn't tell you anything about the distinctive features that the model made. And what's even worse, this happens across many explainable AI methods. For example, this is across a method called GradCam. This is across a method called LayerCam. And this is, it also happens across different models. So regardless of the classification model, this also happens. So here I'm taking two completely different classification models and we can see the same thing. So these are obviously not really helpful. So they indeed tell us where the model is focusing, but they don't tell us what the model is focusing at exactly. So what we really need to answer is what? What are the distinctive features? We don't really want only where. So here, for example, I'm going to switch to images of dogs. So here we want to answer which specific features of the dog were important. I just don't, here it tells me that it's looking at the dog's face, which is very good, but this is not really helpful for me because I can't understand what specific features of this face were important. Is it the shape of his nose? Is it the ears? Is it the body? Is it the head? Is it the snout? We cannot really answer this with simple attribution maps. So the solution to this is to shift towards visual concepts. So here are what we call visual concepts. Each color you see here is a concept. So here we see that there are 4 important concepts for this image, or for this classification, basically, for this model: the ears, the head, the snout, and also the body of the dog. And then we ask another question: is it enough to have visual concepts? And the problem is that if you only have visual concepts, then this is very ambiguous. For example, if you take a look at the concept in green, which is basically representing the snout, what you can ask yourself, what is really important in the snout? Is it the shape that was important, the size of the snout? Is it the color of the snout, the position of the snout? You really don't know this. So we don't just want visual concepts, but we also want multimodal concepts, which are basically visual concepts, but also annotated with text. So here, in this case, every visual concept represented by a different color is going to be annotated with a text representation of it. So here, for example, we can see that the snout is represented by a long snout. So we can see that the shape or the size of the snout is what's really important. And I'm going to call these as textual concepts. And these are basically just descriptors, short descriptions in natural language. They describe many objects in the world. And how we get them is through large language models. But I'm going to skip this maybe because we're running a bit out of time here. But the main idea is that you just use a large language model to gather these concepts. And at the end, what we have is a huge set of around 4,000 to 5,000 concepts. And how do we extract the visual concepts right now? So given a set of images here, we're going to run them through the vision encoder and get a feature representation for each patch. So n here is simply the number of patches that you have for each image times the number of images. And then we're going to basically apply spectral graph theory. So we're going to build a graph out of these patches, a spectral graph. And then we're going to basically perform spectral graph clustering on this graph. And if you perform spectral graph clustering, then basically the second non-zero smallest eigenvector is going to represent the most important parts of the graph that separates the graph into two parts. So the most dominant or the most informative image regions will be encoded in one cluster of the graph, and the non-informative regions will be encoded in another cluster. And then we have these eigenvectors, which we can, now we know where the model is focusing. And then in order to know what the model is focusing at, we apply clustering or principal component analysis only on these regions that were important. And then we have this, and what we can do is simply name these visual concepts. So basically we have a textual bank and our visual concepts, and we're going to simply query every visual region and find what text it corresponds to. So you do this for every region, and how we do it is by a technique called the red circle method. It was published a year ago in ICCV. It simply says that you draw a circle around the region of interest, and CLIP will shift its focus towards that specific region. So you do this for all the visual concepts. You query from your CLIP language encoder, and you get the corresponding concept here. Of course, you do this for all the visual concepts. And here you can see that we've managed to build multimodal concepts. So we annotate each visual concept with its corresponding text here. Yeah, these are just some examples. And then, of course, we perform evaluation on these multimodal concepts. These are just some matrices in Explainable AI to evaluate how good your explanation is. And we also perform clip classification with description. So this is the normal paradigm we saw for clip, that how it performs image classification. And now what we're going to do is we're not just going to use the class, but we're also going to use the detected concepts for each class. We're going to use them as additional information to build our classification layer. And when we do this, we see very impressive improvements in zero-shot accuracy across all the clip models, which verifies the effectiveness of these concepts. And the second point that I would like to discuss is how can we make these image classifiers interpretable. So basically, the question that we want to answer is, what do the vision and language encoders of clip learn in common, which cause the image text points to be closer or further apart in the joint space? We have the vision encoder here, which encodes our image, and we have our zero-shot prediction. We encode it through the language encoder, and we have this joint space. So this is what we want to answer. What basically was learned in common by both the vision and the language encoder, which basically cause these 2 points to be close or further apart in the joint embedding space. And when we say learn in common, we mean by mutual information. So we would like to analyze the mutual information, the relationship between the vision and the language encoder, or what they both learn, or what one knows about the other, in order to analyze how this zero-shot prediction is made. And of course, we can draw a very nice analogy with information theory. In information theory, we have an information channel which connects 2 different sources of information. Here we have a vision language information channel. And we're going to basically enable this by the multi-model concepts that we did. And remember that our multi-model concepts are discrete. Okay, they're not continuous, they're discrete. So they can simply represent bits of information. So what we do is we take our multi-model concepts that we did. These are basically the concepts that the vision encoder knows about. But now the problem is we don't have the concepts that the language encoder knows about. And how do we get this? And we're going to use the same set of textual concepts to do this. So we're going to use the classifier space itself to find the concepts around its prediction. And this can simply be interpreted as a cluster, where in the center you have your predicted class, and around it you have all the textual concepts that are basically representing this class. So we have these textual concepts again from the vision encoder, and then we again find the points around the zero-shot prediction. These are the concepts in the language encoder, and then we can simply find the mutual information by simply seeing the overlapping concepts. So here we see that the muzzle, the snout of the dog is basically what's important for the zero-shot prediction and what causes points to be closer or further apart in the joint space. This is the very basic idea. I don't really want to go more into the math and the results. I think they're a bit boring, but this is the main idea. Once we can have a shared textual interpretation of both the vision and the language encoder, we can identify what concepts are shared and build the mutual information without any approximations directly in the discrete space, which makes it much, much, much more efficient than variational approximations of the mutual information. I've prepared these in case I have more time, but I do not, so I will skip them. And finally, the code is available on GitHub. You're welcome to try it.
Fantastic. So we do have time for a few quick questions. The first one, which came early in the presentation: what is the best technique to get rid of watermarks so that you don't affect vision models?
What is the best technique to get rid of watermarks?
Correct.
In my opinion, a watermark is something you basically have in your original image source. The only way to do this is by simply cropping out the region where the watermark is. You can simply use an image and painting model, for example, after you crop out the watermark region. But this is a bit difficult because, first of all, you need to train a model which can detect whether your image has a watermark or not. And then after doing this, you would have to train another model, like such as Stable Diffusion, which crops out the watermark manually, and then replaces it with some other region using some other regions using some image and painting technique. So it's not really straightforward.
And then these three questions, I believe, came during your first motivation section of your talk, specifically around heat maps. So how is an image importance heat map computed?
There are many different ways to compute these heat maps. The most simple way is so you can use activation-based information. You can simply look at the activations. You can use the gradients, and this is exactly what GradCam does. So if you take the gradients of your predicted class with respect to your image features, or sometimes with respect to your input pixels, then it tells you how important the pixel or the feature is towards the prediction. So it tells you if you nudge this pixel a little bit, how much will your prediction change? There are many other methods, like some of them are black box method. You don't need any activations or gradients to perform this, which are based on occlusion. You simply mask out a specific part of the image. You forward it to the model, and you see how much your prediction drops. If it drops a lot, which means this masked region was very important. So there are many different ways to get these heat maps.
And then we'll take one final question here. How are two heat maps corresponding to two closely related classes, for example, African elephant versus Indian elephant, for example, different? Which aspect of the heat map is used to distinguish the classes by the machine?
Yes, that's the problem. If you use heat maps, you cannot really distinguish which regions were important, because these heat maps, they simply tell you where your model was looking at. It tells you the almost the whole region, the whole object. It just simply highlights the whole object. It doesn't tell you what it's looking at, so you cannot distinguish what the model is really looking at. You can only see where it's looking at. You can only see that it's looking at the main object, but you cannot really see what exactly in the main object it's looking at. And that's the major problem with heat maps.
All right, we'll take one last question here. A burning desire came in. How do you evaluate if the extracted concepts from both the image and text are actual matches or are closely related?
Yes, thank you for this question. This is I did not have time to cover this in the slides, but we do perform a huge evaluation over many different models and pre-training data sets and model sizes and many different things. We do perform extensive evaluation to show that actually the mutual information is really correlated with accuracy. So this can be one way of evaluating the mutual knowledge. If basically it correlates with accuracy, that means it has a stronger mutual knowledge.